Alright, so let's look at an example for our mechanistic steps. We have an overall balanced equation. 2NO2 plus F2 goes to 2NO2F. We want to look at our kinetic data, our rate law, and our two-step mechanism to determine if this mechanism fits with the data that we have. So remember the three requirements for our mechanism. The first is that all of our steps add up to the overall balanced equation. The second requirement is that each of our mechanistic steps be either unimolecular or bimolecular, at worst term molecular. And the third guideline that we have to go by is that our rate law for our slow step has to match that of our overall reaction. So let's look at adding up our two reactions first, our two steps, to determine if this gives us our overall equation. So we have NO2 plus F2 producing NO2F plus F. In the very next step, that red F gets used up, so that red F represents our intermediate and would be crossed out. We need a second molecule of NO2 to interact with that F to produce NO2F. So since the red F is our only intermediate that gets crossed out, we end up with 2NO2 plus F2 gives us 2NO2F. So that's our balanced equation that we have. Second guideline is our molecularity. Both of our steps are bimolecular. Both of them require a collision between two different molecules. And then our third requirement is our rate law. So if we look at our rate law that we're given from our kinetic data, we have first order for NO2 and for F2. Only step 1 shows us the same kind of rate law, where we have NO2 colliding with F2. So step 1 must be our slow step because it matches our rate law for our kinetic information. We can also get the same kind of kinetic information about our slow step from a reaction graph. So remember on the reaction graphs, we have energy along the y, and we have progression of our reaction along the x. So from our reactants, NO2 and F2, we have an increase in energy to our transition state, requiring our activation energy amount. Then energy decreases as we go to our products, but this would be the products of step 1. And then step 2 begins immediately. And step 2 has a separate activation energy that's not at all the same as step 1 to get to a second transition state. And then energy decreases down to products. So we have two steps we can tell from the two transition states. We have two different activation energies that go along with the two steps. The first step has a much greater activation energy, indicating a slower reaction, compared to the second step, which has a much shorter activation energy. The greater the activation energy, the slower the reaction is going to go, because less of the fraction of molecules will have that sufficient energy to make product. If you have a very small activation energy, more of the fractions of molecules will be able to have this sufficient energy to make product, and your reaction will go faster. Now for each of the steps, we can see the endothermic and exothermic shape. So step 1 is endothermic, but step 2 is very exothermic. Overall, the entire reaction would be exothermic, and our delta H noted here would be negative. What if the first step wasn't the slow step? Let's look at the slow step being the second step. So if I have 2NO plus Br2 produces 2NOBr, and I'm given the rate law for this reaction, where rate is equal to K times NO2 squared times NO squared times Br2, telling me that NO is second order and Br is first order, we could write a mechanism indicating one step, but that would be termolecular because we would have two NO molecules colliding with a Br2 molecule, which doesn't normally happen. So this suggests this is at least a two-step mechanism. So let's look at our two-step mechanism, where we have one molecule of NO interacting with Br2 to produce NOBr2. Then that NOBr2 as an intermediate interacts with the second molecule of NO to produce our products, NOBr. In this mechanism, our first step is labeled as fast, and our second step is the slow step, indicating step 2 is our rate determining step. Now if our second step is slow, let's imagine what's going to happen at the molecular level. Step 1 has to occur first and happens very fast, so we have this buildup of NOBr2. But since the second step is very slow, the NOBr2 is not being used up very quickly. So this means that step 1 will start breaking down the NOBr2, and it will start moving it backwards. So we can't just stockpile this and wait. It will start breaking down and going back the opposite direction until we reach an equilibrium. So this indication here, the double-headed arrows, indicate an equilibrium is reached, where NO plus Br2 is creating NOBr2, and the NOBr2 is breaking back down into the two molecules NO and Br2 again. Now our rate determining step is step 2, which is the slow step, and this would be dependent upon an intermediate. The amount of NOBr2 that we have would be part of our rate law, and then the second NO molecule. Both of these would be first order based on the collision idea of a biomolecular reaction. Now we have a problem though. We can't base this on the concentration of an intermediate, especially one that is breaking back down into its substituents. So what do we do about this? We can't leave our rate law as our K times NOBr2 times NO, because we have no way of measuring our NOBr2 concentration. So we have to substitute our NOBr2 concentration for something else. We need to base our NOBr2 on the amount of NO and Br2 that we have. So we're going to create a system of equations in order to substitute for it. Since step 1 reaches equilibrium, the rate of the forward reaction must equal the rate of the reverse. So we're going to use that idea to set up our equations. So we're going to say the rate of the forward reaction is based on K times NO times Br2, and then the rate of the reverse reaction, K to -1, just indicates that it's going backwards, times NOBr2, which would be the reactant of the reverse. We set those two equal to one another. We're solving for NOBr2 so we can substitute it in. And when we do that, we divide by our K minus 1 to give us our ratio of Ks times NO times Br2. We're then going to substitute that into our previous rate law expression. So our NOBr2 is really equal to our K1 over K minus 1 times NO times Br2. So this part right here was what we called our NOBr2. And we're substituting it in, so multiplying it by the K2 and the NO from the previous equation. Then collecting our terms, we have NO squared times Br2. So this matches our kinetic information. The last thing we want to talk about with mechanisms is catalysis, using a catalyst to speed up the rate of a reaction. So a catalyst can be any substance that increases the rate of a reaction. In biology, this is normally referred to as enzymes, using large proteins to catalyze a reaction. In chemistry, though, we can use small molecules as catalysts. We can use metal surfaces as catalysts. We can even use gases as catalysts to institute more collisions. Now, a couple of things about catalysts. Catalysts do not make more product. They make the reaction faster. And the way they make the reaction faster is by finding an alternative route that has a lower activation energy. So if you remember, the height of the activation energy on our graph, or the extent of activation energy, really can determine how slow our reaction is. The larger the activation energy, the slower it's going to go. So if we can come up with a pathway that has a lower activation energy, our reaction will go faster. So that's what a catalyst does. It provides a second route to our products that has a lower activation energy. Now in the graph here, our activation energy is lower because we have 2 steps in our catalyzed reaction, as opposed to the 1 in our uncatalyzed reaction. It doesn't always have to produce 2 steps. It could still just be 1 step, but the activation energy has to be lower. So these are our 4 different key requirements for a catalyst. Catalysts must increase the rate of the reaction. That's their whole point. If they're not increasing the rate, they're not really doing anything. They cannot be produced or consumed by the reaction. So when we look at writing out our mechanism, our catalyst cannot be something that is being produced, like an intermediate. It cannot be consumed, like an intermediate. Catalysts are put in at the beginning of the step, and they come out at the end. Right? Since they are not consumed, a very small quantity of catalyst is all that is needed to catalyze a reaction, because you're not using it up. So you don't need a ton of it. And the last point, catalysts speed up the rate of the forward and the reverse reactions. You cannot speed up one direction only. When you're using a catalyst, because it lowers the activation energy, the reaction can go forward and reverse faster. Alright, so we can see this from the graph. Red line represents the uncatalyzed reaction. The green line represents the catalyzed reaction. We can notice right away a difference in the number of steps. The uncatalyzed had 1 step. Catalyzed reaction has 2 steps. Alright, and our 2 steps also show a lower activation energy compared to the uncatalyzed reaction. So this reaction will go faster even though it's more steps. Now, something that doesn't change, delta H. We started in the same position for our reactants. We ended in the same position for our products. So our delta H is exactly the same. It doesn't matter whether we have the uncatalyzed or the catalyzed reaction. Delta H has to stay the same. Potential energy of our reactants, potential energy of our products has to stay the same. The only thing that changes is the activation energy required. Now, the uncatalyzed reaction is always possible. So we're not permanently altering the reaction process. We can always do it the slow way. The catalyst just provides an alternative pathway that is faster. And this is what a catalyst would look like in the reaction mechanism. The uncatalyzed mechanism is on the left. We have H2 going to 2H. Then we're using those H's to interact with C2H4 to add hydrogens to the carbon chain. to eventually make C2H6. In the palladium catalyzed reaction, we see palladium put in at the beginning, so a catalyst has to be put in at the front. We see how it helps produce the H's, and then it allows the H's to be added to the carbon chain more effectively until it comes out at the end. And it comes out the same way it went in. So it's not being consumed, it's not being produced, it's not an intermediate, and you'll notice it does not show up in the overall balanced equation either. So from the overall balanced equation, you would not see that a catalyst was used. It's only shown in the mechanism, or sometimes people will write it above the arrow if there's a catalyst. Alright, so that's the end of mechanisms.